Okay, so this is 10.12, manipulation of series. A lot of the manipulating of series that we're going to do today is following this chart here, where we have sine x, cosine x, e to the x, 1 over 1 plus x, 1 over x, natural log of x, and arctangent of x. We need to memorize 6 of the 7 here, like I said. Okay, the ones that we need to memorize: sine x, cosine x, e to the x, 1 over 1 plus x. This is the general power series. This one is the general power series. 1 over x, natural log of x, and arctangent of x. Okay? And then these are just the intervals of convergence. And it's a good idea to memorize these so that way you don't have to go and try to figure it out. You're going to spend a lot of time. Now, where do these come from? These come from actually doing Taylor polynomials to it and finding the Lie coefficients. Okay? If you look at each of these functions, they're all centered at 0. So these are Maclaurin, they're Maclaurin series. Okay, cool. So what we're showing here in this lesson is manipulating series. We're going to take series that we know, these 6 that we know, and we're going to manipulate them in such a way. So for instance here, this is the general power series. This is the general power series. Okay. And if we know the derivative of, let's say, our such power series, we can integrate this guy, and you'll notice that he's starting at n equaling 1. And when we integrate it, we're going to n equaling 0. And the reason why is because we're going a term backwards. So pretend like you have the derivative. You have the derivative of the power series, and when you take the antiderivative, you're going a term backwards. Okay? Just like when we had derivatives. We're going basically, if we want to take the integral, we're going backwards. Kind of like if we had velocity, we're going to position. If we had acceleration, we're going to velocity, and then from velocity, we're going to position. Okay? And so this n equaling 1 is going to change to an n equaling 0. And then we put a plus c, obviously, because this is a definite integral. Okay? It's the same principle that we apply when we take antiderivatives. So you're going, if you take the antiderivative of this, you're adding 1 to the exponent and dividing by that 1. Okay, so notice here that this is n minus 1. You're going to substitute an n, you're going to substitute a plus 1 to this guy, and then you're going to bring him to the front. You're going to divide. Okay? So for instance, I have here f of x is the series of x over 2 to the power of n. Looking at this guy, he has the characteristics of a geometric series. X over 2 to the power of n. It says find f prime of x and find the integral of f of x dx and the interval of convergence for all 3 power series. So if I want to take the derivative of f of x, I'm going to subtract 1 from the x. I'm going to bring the n in front, subtract 1. So you'll see that that's what we should have done. Where is it? Right here. So what I did was I brought n to the front, and then I subtracted 1. And so when I look at this here,
Yeah, why is it n over 2?
yeah, we're trying to, let me figure that out, n over 2. I think the reason is because we have to consider the previous term. We have to consider what came before it. So when we had f of x, it says, yeah, it's from n equaling 0. But if you're taking the derivative, you're going a term back. You're going a term before that. So what term came before x over 2 to the power of n. So for instance, let's say if my series starts at 2 comma 4, let's say our series starts at 2 plus 4 plus 8. What came before 2? Not 0.
2, oh, 1.
1.
You're multiplying by 2.
You're multiplying. Okay? And so this is kind of like that idea that we're going a term backwards, because if I plug in 1, this would leave us with n to the power, this would leave us with 1/2. So because that's starting at the 0th term. Okay.
Mr. Martin,
Yeah.
can you explain taking the term like 1 to 4 again? I don't get it.
Okay, so like when you subtract 1 from when you have this, you have x over 2 to the power of n, right?
Mm-hmm.
You're gonna take this whole thing and you're gonna bring it to the front.
X over 2?
The n over 2. You're gonna take, because if you
It's just a derivative.
it is, but she's asking why is this n over 2?
No, I was just asking in general, why are we taking the term before? Uh-huh. Yeah.
Because you're subtracting 1 from the n, you're going back a term.
Uh-huh.
By subtracting 1 from n, you're going back a term, so then that leaves you with what was that term before?
Okay.
It'd be like n over 2, because you're dividing by 2 every single time. Okay?
Oh, I finally get it. Okay, got it. So, if the pattern was like multiplying by 2, would it be 2n then?
Yeah.
Okay. It's like 1. It's 1/2.
Okay, so this is basically taking the derivative of f of x, and it looks like this. Okay? And then they did some partial sums to this, right? They plugged in 0. Yeah, they plugged in 0, and obviously the first term would give you 0. And then they plugged in 1. If you plug in 1 in for n, you're going to be left with 1 minus 1 is 0. Anything to the power of 0 is 1. 1 times 1 over 2 is 1 over 2. And then we went to the second term, and we wrote out the partial sums. Okay? Now, what we're doing here is we're trying to see, is it convergent at the endpoints? So we're going to start with n equaling -2. And the reason why we start with n equaling -2 is we're doing a ratio test. We're setting x over 2 so that it's less than 1. Okay? And so when we set that less than 1, we show that this is our interval of convergence, -2 to 2. So we're going to test -2, and we're going to test +2 by plugging it into our series here to see if it comes out convergent or divergent. Well, since you plug in -2 into here, you're going to get -1 to the power of n, and well, actually, you could just plug it in here. You would plug plug in -2 in for x. Yeah, if you plug -2 in for x, you're going to get a -1 to the power of n minus 1. And you could obviously see there that it is divergent. Okay, because the numbers are they are alternating, but they're also getting larger each time. Okay, so it would fail the alternate series test. And so this is also, you could do an nth term test of divergence too, to see. Okay, and then obviously if you do it to 2, it's the exact same thing. Okay, so our interval of convergence is going to go from -2 to 2. Now, when we integrate it, when we integrate, we're going to take we're going to add 1 to the exponent, and then we're going to divide by 1/2. And when we divide by 1/2, it's the same thing as multiplying by 2. Okay, and then there's an n plus 1. What was that?
Can you do it?
Yeah, sure. You're going to have to write this for me. I'm going to have a hard time. So, okay, so I have f of x is equal to, what was that, x over 2 to the power of n?
Yeah.
Okay, so if I want to take the integral of f of x dx, that's equal to taking okay, and so what I'm doing here is I'm going to add 1 to the exponent. So I'm going to add 1 to the exponent. So we have x over 2 to n plus 1. And then I'm also going to take in consideration that this is a 1/2. So you could like pull out a 1/2. So I could pull out the 1/2, and that would be the same thing as multiplying by 2. So it's like dividing by 1/2, but you're multiplying by 2. You're multiplying by the reciprocal. So this becomes 2 over n plus 1. Okay, and then this is plus c. Okay, so that's what I got. And then this is the series for that. Okay, so this is n equaling 0 of 2 times x over 2, n plus 1 over n plus 1 plus c. Okay? And then you could do, obviously, the interval of convergence. Okay? And so I have that. They also, it looks like we simplified here. No, we didn't simplify it. We're just doing our interval of convergence at -2 and 2. Okay, so if I did -2 and I plug it in for here, I get this guy here. And I can see that my terms, when you do a partial sums, I can see that my terms are getting smaller. They're alternating, but they're getting smaller. So this would be considered alternate series, and it would be convergent. But if I plugged in 2 in there, I get a harmonic series here. This is an example of a harmonic series. Okay? Now, if this was on a free response question, you can't just say that this is a harmonic series. You would have to do an integral test to show that it's a harmonic series. So right here, if it were on free response, you would need to do an integral test of 2 over n plus 1. Easy. Easy. You're just going to integrate 2 over n plus 1, and you're going to show that it goes to infinity, which means it's divergent. Thus, it's harmonic. Okay? That's only if it's free response. If it was multiple choice, you're just going to, they're not going to know. You're going to know that that's harmonic. Okay? I say that because in tons of message boards right now on Facebook and Reddit, they are putting a lot of focus on this. They're putting a big focus on if you see a free response question where they have, where they ask you if it diverges, you need to do an integral test to say that it's harmonic. Does that make sense?
Yeah.
Okay. I'm just saying, the calculus community is blowing up over that. Very nerdy, but yes. Okay. Because everyone right now is in the same spot. Like all the teachers, they're teaching this stuff. But we're ahead because what they did, what a lot of teachers are doing is they're covering polar and parametric at the end. We covered it near the beginning. So we're actually really ahead. Well, that's what the next 2 months is for. Okay. So these are the functions we need to try to memorize. Okay, because it's going to make our life so much easier when we are doing the rest of this lesson. So it says, using the Taylor series, show that the derivative of e dx is e dx. And if capital F of x equals the integral of e dx dx with f of 0 equaling 1, then capital F of x equals e dx. So what we're doing is we're taking the derivative of e dx. The derivative, e dx as a Maclaurin series is up here, okay? So we're taking the derivative of this. And so when we take the derivative of 1, that's 0. If we take the derivative of x, that's just 1. And then we're just taking the derivative of each of these individual terms. And we end up getting this, okay? You're just doing a power rule, okay? And so when we do this, we end up getting this, okay? Now this right here is basically what we started off with,
Yeah, it's like,
right? It's basically what we are starting off with. And so the derivative of e dx is e dx. Okay, so that's kind of how they're proving it, is that even if you took the derivative of each of these terms here, it still leaves you with what you had started off with, which is e dx. Okay? Now, they want you to show that the integral of e dx is equal to e dx. So this time, you're going to take the integral of your power series, or your Taylor series, or whatever you want to call it. This is the power series. So you're going to take the integral of this guy, and you will notice that when you plug in the point 0, 1 in for x and in for y, you're going to get c is equal to 1. So if you plugged in 0 in for all the x's, you obviously got 0 plus c is equal to 1. Remember, you're plugging a 1 in for f of x, and you plug a 0 wherever you see an x. Okay? And so all these are going to come out to be 0, and you have c is equal to 1. Okay? So now that we know that, we got 1 plus x squared over 2 plus x cubed over 3 factorial. And guess what that is? That's the exact same thing as what we had here. Okay? Which one? Well, 2 factorial is the same thing as 2 times 1.
oh, yeah.
I mean, you could put it, but it just means 2. Okay. So that's that. Okay. Now we're gonna manipulate the series that we have memorized. We know that sine x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So what we do here is, if we have sine of 1/2 x, we're going to replace all the x's with 1/2 x. That's all we're going to do. We're going to put 1/2 x wherever we see an x into our parent function. Okay, and then we're going to try to simplify. Okay, so you're going to plug in wherever you see an x, you're going to put in 1/2 x or x over 2. Okay, because that's the same thing, right? X over 2 is the same thing as 1/2 x. Okay, and that's what we did. We do that to every single one of the terms. And does that make sense? Okay, so why are we doing that? Well, the reason why we're doing that is because it's going to save us time instead of actually doing a Taylor polynomial. Notice here on the left side, I did a Taylor polynomial using sine of 1/2 x. And that's a pain in the butt because it's a lot of chain rule. You see that? There's a lot of chain rule. So left side, a lot of work. Compared to if we know the parent function, we replace what x is, that's that 1/2 x, in for here, it's going to save us time. We won't have to do all the derivatives. Okay? Yeah. So this is the part of calculus that sucks because you're having to memorize. Okay? But we're memorizing because we know how to do this by doing Taylor polynomials. Okay, look at cosine of square root of 2x. You're going to replace wherever you see an x, you're going to replace it with square root of 2x. So you'll notice here that, where is it? Wherever you see an x, I'm going to replace it with square root of 2x. That's why it's so important that we memorize our 6 functions. Okay? Our 6 functions. Okay? Look at sine of x cubed. You're going to replace wherever you see an x, you're going to replace it with a x cubed. And then you're going to try to simplify a little bit. Okay, so looking at sine of x, we're going to replace our x with an x cubed. So you're going to replace this x with the x cubed, and then you're going to distribute with the exponents. So that gives you 6n plus 3. And so you'll see that's basically what it is, 6n plus 3. Over 2n plus 1 factorial. Okay? You see that? Wherever you see an x, you replaced it. Okay? Same thing with e to the negative x. Wherever you see an x, you replace it with negative x. Okay? Now this one's a tad bit different. Easy, because if we know e to the x, we're just going to multiply every single term by x squared. So we know that e to the x is 1 plus this. We're just going to multiply every single term. That's just a law of distributing by x squared. And so we get this guy here. Okay? And so basically that comes out to taking this guy, replacing him, or multiplying him by x squared. And so that way you have x, what is that, x, replacing with what, x squared? So you have x times x to the power of n. So that gives you x to the power of n plus 2. And remember, if you have like bases, you add the exponents. Okay? Okay, look at this one. This is a combination of our two guys here. We have 1 over x, and then we have arctangent. Okay, so we have here, arctangent goes on the top, and on the bottom is the 1 minus x minus 1 plus x minus 1 squared minus x1 cubed. And so that's what we did. We put it on top of each other. Okay, we know that here, arctangent is this. You could do it like that, or you could just do arctangent over x. So all the values, and then you're subtracting an exponent every time. Right? So you could take here. We have arctangent of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, dot, dot. And we could just divide every single one of these terms by x. So you're dividing every single one of these terms by x. And so this would end up being 1 minus x squared over 3 plus x to the 4th over 5 minus x to the 6th over 7 plus dot, dot, dot. Right? There you go. Okay, and then this one is just a combination of multiplying by x and then replacing all the x's for cosine with x to the power of 3 halves. Okay? Any questions on this? Okay. Now, an important power series is the general power series 1 over 1 plus x. That's this guy here. Okay? Now, I have a general one that I learned when I learned calculus, and that one is 1 over 1 minus x. This one is special because it's not going to alternate signs. It's just going to be 1 plus x squared plus x cubed plus x to the fourth plus dot, dot, dot until we get x to the power of n. Okay? So this is even 1 over 1 minus x is even more general than 1 over 1 plus x. Now, how did that come about? Well, 1 over 1 plus x is the same thing as 1 minus negative x. So what I'm doing here is I'm replacing all of my x's with negative x. And so all these become positive. You see that? So some teachers will teach you that the general power series is 1 over 1 minus x, but here I have 1 plus x. Okay, because a lot of times they'll have this on the AP exam like this. Okay. Okay. So do we understand 10? Wherever we see an x, we're replacing with 2x. Wherever we see an x, we're replacing with the negative x, x squared, and then this guy's multiplying by 4x and replacing the x with 3x. Okay. So find the power series for f of x equaling 1 over 1 plus 2x. So you just need to make sure you know the general power series here. Okay, and you're going to replace all my x's with 2x's. So you'll see here that I replaced all my x's with 2x's. And then we're just going to simplify. Okay, you can simplify maybe the first 4 terms. See how this simplified into 4x squared. This simplified into negative 8x cubed. And so you have that. Okay? Do we need to go through any of those? Are we good there? Okay, so it says use the power series for f of x of 1 over 1 plus x to find the power series for arc tangent of x. Find its interval of convergence and use it to approximate the value of pi. Okay, well, you have here 1 over 1 plus x. If I know anything about arc tangent, what's related to, how is 1 over 1 plus x related to arc tangent? Yeah, isn't the derivative of arc tangent what?
1 over 1.
1 over 1 plus x squared. Okay, so what we're going to do here is if we know that the derivative of arc tangent is 1 over 1 plus x squared, we'll take the integral of 1 over 1 plus x squared, and that will equal arc tangent of x. You see that? And we already know, we know how to find the power series for 1 over 1 plus x squared. Because we know that 1 over 1 plus x is right there. Where is it? Right there. 1 minus x plus x squared minus x cubed plus x to the fourth, dot, dot, dot. Right? And we're going to replace all the x's with x squares. And then we're going to integrate this guy. And by integrating that, that's going to give us arc tangent of x. Pretty slick. Okay? And so that's what happened here, is that we are going to integrate this guy, and we'll end up with this. Okay? We're adding 1 to each of the, we're adding 1 to the exponent and dividing by n plus 1. Okay? Cool. So that's that. Now, then the next thing is find the interval of convergence. So what you're going to do is you're going to take this guy that we have here, and we're going to set this so it's less than 1. Okay, and then you're going to do a ratio test. So you notice here we're going to do a ratio test to see what its interval of convergence is. And so its interval of convergence will come out to -1 and 1. We'll have to test those endpoints. We'll have to test -1 and +1 to see whether or not converges at the endpoints. And it does. Like, I mean, that's why we memorize arc tangent of x too, because you wouldn't want to spend all this time doing this on a test. Okay. Okay, so find the first 4 non-zero terms of e to the x cosine x. So this is where it gets a pain in the butt. Because now you have e to the x and cosine x, you're basically multiplying these two power series together. Okay? So, and they want the first 4 non-zero terms of e to the x cosine x. So you're going to have to FOIL this out.
No.
Okay?
No.
You're going to have to FOIL it out.
But yeah, how would that even work?
You're gonna take 1 and multiply into this, 1 into this, 1 into this. You'll start to see a pattern that things will cross out. Okay?
Okay, and then what do you do?
That's it.
What's the
You
point of
FOIL and combine like terms.
And then?
And then that's how you find.
Those are the first 4, non-zero. Oh.
Yeah.
I'm not, okay.
Okay, so it's just a lot of foiling.
And then 6.
Which find the first 6 non-zero terms of sine x. That one's not it's not too bad. Okay, but again, that's also foiling, and it's a lot of foiling. Okay? So I'm just saying, if you come across any of these, you're going to have to do some serious foiling. Okay, so this next number 18 is asking you use trapezoidal rule to approximate the area under the function f of x equals e to the negative x squared on 0 to 1 with 4 trapezoids with equal bases. Then use a power series for the same approximation for the error of less than 0.001. Now the reason I put this example is because in statistics, this function is the example of the normal curve. This is the normal curve. This is the function that represents our bell-shaped curve on a normal distribution. Okay? And what's painful about this is that you can't just, because you want to find the area underneath the normal distribution curve, you can't integrate that using U substitution or partial fraction, or what is it called? Integration by parts. E to the negative x squared, you can't do it. So what we do is we do an approximation using series. Okay? Because we know that e to the x is that. So we'll replace all of our x's with negative x squares. Okay?
With what?
We'll replace all of our x's in e to the x with negative x squares.
Okay.
Okay? And they want a trapezoid with four trapezoids with equal bases. Okay, well, our interval is going from 0 to 1. So our lengths, if they want 4 of them, our lengths are going to be 1/4, right? Our lengths each time are 1/4, and our
Could you draw the thing?
was that?
Like, could you draw it? Because
Can
I'm
I-
having a hard time picturing what they mean by 4 possibilities.
Yeah. Oh my gosh. Okay. So like you're gonna do a bell-shaped curve. Okay. And they want the area from let's just say like 1 to 0, right? Here's 0, here's 1.
And then 4 trapezoids.
And then they want 4 trapezoids. So here's okay, and so on. Okay, you're gonna have 4 of them. They should be equal length. Okay, so this one's gonna be that 1/2. This is, I'm sorry, this is gonna be 1/4. This is gonna be 1/2. This is gonna be 3/4 and to 1. Okay, and you have trapezoids here. Why is this? Where did this go? Okay, hold on. Okay, there we go. So there's our first trapezoid, and then our second trapezoid, and then our third trapezoid, and our fourth trapezoid. Okay, and so the integral from 0 to 1 of e to the negative x dx is going to be approximately,
Wasn't it negative x squared?
yeah, it's going to be approximately 1/4 times,
I think you put 1/2. No, after the 1/4.
yeah,
It was 1/4 times 1/2.
but we got to understand where the 1/2 came from. So 1/4,
Are we using the formula for the trapezoid?
yeah, it's 1/2 of the length times, yeah, so it's 1/2 times 1/4,
Wow.
okay, times, and then we have to do what this guy is, e to the negative x squared. So we know that e to the x is 1 plus, so this is going to be 1 plus x squared plus x to the 4th over 2 factorial plus, what is it, x to the 6th over 3 factorial plus x to the 8th over 4 factorial. Oh, wait, we're supposed to have negatives. That's okay. Well, they all become positive,
Okay.
right? Because if you have negative x squared and you take it to the power, yeah, they're going to all become positive.
So do you think the derivative of that?
No, this is the approximate. This is going to be the approximation. Okay, and
So
so
is that the derivative series? Like you're already deriving?
you're doing an approximation of the area under the curve.
Oh, so we don't need to.
We don't need to take derivatives. We just need to basically evaluate this from 1 to 0. It's not too bad, like in the sense that, like, if you plug 0 in there, you're only going to be left with 1 times 1 over 8. But then you have to plug in 1 to all of this. Okay, and so I think this is where the calculator comes in. Okay, so if you used your calculator, the answer comes out to 0.747.
Oh, but they plugged in E. They have E.
Where?
Like everywhere, and we don't have E. I think you put in X's. Oh. Look at their series, and then look at all.
It's because they're plugging it in for, but we have it right here.
Is that them figuring out the error?
Oh, that's the error, yeah.
Yeah.
Oh, because they're finding the area under each of the trapezoids for the bases. So base 1 and base 2. If you plug,
Yeah, I don't know how they got that or the.
okay, well, let's start with this. We know that e to the negative x squared is going to equal what? 1 plus
1 minus x squared.
1
Wait, 1 minus
1 plus negative x squared
plus
plus
negative x squared.
negative x squared over 2 factorial plus negative x squared cubed over 3 factorial Oh, you know where they got it? They did the bases. They plugged in the value at 1/4. They plugged it into here. Like in order to find the area of the trapezoids, they took what's base 1? 1/4,
Okay.
and they plugged it into e to the negative x squared. You take 1/4, that would give you e to the 1/16.
And then where did they get the 2? It's 2.
Because there's 2 of them. Because when you do the other base, that it shares another base. Base 1 and base 2 are gonna then change based on the trapezoid. Here, we need to write it all out. It's gonna take 20 minutes to write it out.
That's a complicated problem.
Okay, so trapezoid is you take the parallel sides. What's this length? E to the
Negative
e to the 0 is
Oh.
1. Okay. Plus base 2 is e to the negative 1/4 squared.
Okay. Yeah, that's E to the 1 of the 2.
Yeah. So this is e to the 1/16. Okay, that's the first base. Let's go to the second. Let's go to the second trapezoid now. The base 1 is e to the 1/16.
And then you plug in a 1/2.
Plus, now you're going to plug in a 1/2 into there. And so that's going to be what? E to the 1/4? Well, I mean, it. If you put 1/2, you're going to get e to the. Okay, hold on a second. We have e to the negative x squared, right? So we're going to plug, we plugged in 1/4 into there. We got negative 1/16. Negative 1/16 gives us 1/e to the 16, right? Yes? Plus 1/e to the 16 plus 1/e to the 4 plus, now we got to do the next one, 1/e to the 4th plus, and you're going to put 3/4. So that's 9/16. So that's 1/e to the 9/16. And you're going to continue to do it until we get to the last trapezoid. But it's a negative exponent.
What is the 9? No, it's inside the parentheses.
It's inside the parentheses.
It's not a different constant.
It's e to the negative 9/16 is the same thing as 1/e to the 9/16. Right? Okay? And there you go. These 2's come from because you're adding 1 over 16 plus 1 over 16, which is 2 over e to the 16. And then you're adding 1 over e to the 4th plus 1 over e to the 4th is 2 over e to the 4th. And then you do it one more time with 2 over e to the 9 over 16. And then the last one's plus e. Because if you plug in 1 into there, you got 1 over
e
plus 1 over e. Yeah,
No,
that's what.
see, look, they don't have any negative.
Okay, hold on. Let's do it. Here, watch. We have e to the -1 over squared equals e to the.
-1. The negative is on the x though, right? But usually if you plug in a value and it's like that, the negative stays outside the parentheses.
I don't know. I'm done with this.
Mr. Martin, we can't stop now.
I think that negative, yeah, that negative is, I guess, being squared.
Okay, no, but if you have a function and it's like negative x squared, right? And then
No,
it asks you to plug in a -2. So you'll do
I agree.
-2 and it'll be 4 and the negative will stay outside and give you -4. Yeah. It's not a positive 4. So the negative does stay outside, but they're just not making it stay.
Yeah, I agree.
Oh my God. Wait, aren't these your notes?
Yeah.
Maybe there's a logical explanation. Yeah.
No.
Wait, I have an idea. Why don't we like add like 1 plus 1 over whatever our equation was and see if it comes out to 1.879. I don't know. Yeah, add like 1 over 6. 1 over e. Because we need to get 1.879. So
I think that negative x, it goes negative x and then all of it squared.
negative x and then really?
Yeah.
Oh. But that is different from like normal
Yeah.
arithmetic, right?
I'll have to look into it.
Oh, but could you go over how to do the error? Because I can never.
So the error is basically taking what's the next term in the series that it's going to be accurate to less than 0.001.
Okay.
So you'd have to find the sum of the first couple terms to see, okay, how much is the error of the next term. So let's say we have like 3 terms. We find the sum of the third term, okay, and then we are going to have to subtract that from what the error is of the 4th term. Okay, and if that value comes out to being less than 0.001, then we say that we neglect that 4th term. Okay, so this is
So how many terms did they use?
it looks like that we used 4 terms. Wait, hold on. 1, 2, 3, 4. The first 4 terms, because the 5th term came out to being 0.008. So it's accurate to the first 4 terms.
So it would be the next term minus the first, like, whatever.
The sum of the. Okay, and that's the rate that would be considered the interval, like the range of the values. It could be whatever this number minus it or added to it. Okay, so you would add 0.008 to this value, or you would subtract 0.008 from this value.
And that would.
And that would be the interval of error. Okay, I think that's really it for these guys. It's just manipulating. This one was a hard one. I will admit that. Okay, you don't need to worry about this. This was just going like if we had time at the end of the year, we could do some crazy stuff.
Imagining.
Oh, this is called the Euler's number. Okay, so like we don't need to worry about that. And then I was trying to derive Euler's formula. So we're using series to derive Euler's formula, but that's okay. We don't need to do that. Okay, I wanted to make it poetic at the end and say like, hey, this is where like the universe comes from. Like this idea of the universe. This is literally Euler's formula. They call it God's formula. But
That's a little
in mathematics, like that's what they call it. A lot of these mathematicians were very religious in their time. Some of them weren't, but some of them were. A lot of the mathematics that we're doing is from a lot of these guys up here. Like this was created by Gauss. The normal distribution curve. They call this the Gaussian curve. Okay, and that's it. That's manipulation of series. Okay, I recommend you obviously do some of the homework over this, and then do the quizzes probably on Thursday, right?
Yeah.
Huh? I'm not.
I kind of have a question.
Yeah.
Wait, would you come here first? So like, okay, you know for like these problems, for like the homework class, and like I know how to do this, but I can't take this and then make it into like a formula.
Try to see if you can see it.
Because like I need this, I can like do all of it, but like I need this in order to like find the interval. But I can't just like look at these and then figure out that it's that.
Yeah, it's not. I'm not expecting.
Okay. Then how are we supposed to do all of these things if I can't even come up with this?
That's why you're gonna memorize the general, like sign
Oh,
X.
oh, I guess this was before that one, huh?
Yeah. So you gotta memorize those. There's 7 up here, but 6 of them you need.
Okay. And then when you have time, could you do an example problem for like the Laurent error? I just the errors are hard.
Okay, can you? Yeah.
Okay, I think
I
it's
got an email from the media center.
Just
Right now?
oh my gosh. Go.
guys, it's actually come on, I need this for the kids.
Okay, what question?
Okay, I think it's homework 10.9 and then maybe
Wait, you said 10.9?
yeah. I think that's the and then
AV, we're gonna start here in like 10 minutes.
yeah, go to like the bottom one. Those ones are the arrow ones.
This one?
No, like all the way down. I think there's one more page. Yeah. Yeah, maybe number 13. Maybe
Okay.
you can explain it.
Here, I'll just do it. We did this example similar.
Is that from the homework?
This is from the homework, but we did do this.
Oh.
Determine the degree of the Maclaurin polynomial that should be used to approximate e to the square root of e to 3 decimal places by using the Lagrange remainder. Use this Maclaurin polynomial to approximate the square root of e to 3 decimal places. Okay, well, first of all, you need to know e to the x, what that looks like.
Oh, now we can do the thing.
Yeah, so e to the x is equal to what? 1 minus x? Or 1 plus x? 1 plus x, and then it goes what? Plus x squared over 2, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial, plus dot, 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 until you get to x to the power of n over n factorial. Okay? So we know that if x is 1/2, all we have to do is plug 1/2 in for x, because the square root of e is equal to e to the 1/2. Okay, so we have 1 plus 1/2 plus 1 over 8 plus 1 over, was that 8 times 3 factorial plus 1 over 16 times 4 factorial plus dot, dot, dot. Okay? What it says, 3 decimal places, use the Lagrange remainder, use the approximate to 3 decimal places by using the Lagrange remainder. This Maclaurin polynomial approximation to 3 decimal places. Well, if we do the first 3 terms, 1 plus 1/2 plus 1 over 8, what does that give us?
Hannah, do you want me to? Yeah.
Well, it's 1.5 plus 1 over, just, no, calculate it.
Hannah, get it out.
I thought she's doing it. Take your time.
No, right?
No, yeah. Hannah, you can do your
Okay, 1.65.
Don't take, huh?
Hey, isn't that what I said? Isn't that what I said?
No. Is that what you said?
Yeah,
Right?
that's exactly what I said.
Okay, so that's the first 3 terms.
Okay.
If we do the 4th term, we're going to take 1 over 1 over basically 4 factorial. Because that's the same thing as this. Here, hold on. 1/2 to the power of 4 over 4 factorial. What is that? What's this value? Just this. If you want to save yourself, you could do
Wait, I got this is 4 factorial.
I have these in here. I don't know.
Okay, it's 0.0.
hold on, no, that's not the 4th term, is it? Yeah, but this wasn't 3 terms. This was 2 terms. Okay, do add 1 over 1 over 64 to this number. Just take 1.6.
1.64. Yes, I got that. Right, come on.
1.6
4065.
1.640 625. Okay, so that's for this.
Okay, first four.
Okay, and then the fifth term, what did you get for this one? 0.00.
2, 6, 0, 4, 1, 6, 6, 7.
Okay,
And so
so you could subtract it or add it, and that would be the error.
Hmm.
Is that what the answer?
No, the answer was just one number. It was 1.6484375.
yeah, I think that was
Okay, so we did from 1/2.
No, after the 4, it's an 8, not a 3. Look, yeah.
oh, okay, then I think
Okay, well, so what they did was they found the errors. Here, look at this. They did the first term. What? How much value? How much the change it was? 2, 3. So this is the third decimal where it's actually this one because it says 3 decimal places. So this has an error. The fourth term has an error of 0.0052.
And they did that by taking the 4th term and subtracting it from the first 3 terms? Or
They're-
just plugging in a 4?
They're taking for n equaling 4. They took the next term in that series, the 5th term, and subtracted it from what the 4th term
so
was.
we gotta go one more.
Oh, okay. And then they added that to our
Yeah.
1.64?
Yes.
Yeah, that makes sense. Okay.
So basically, if you were to do the first 4 terms, you'd come out to this value, which that's what we had. If you add just this to that, you would get what they have there. Okay, so the Lagrange error just finds what's the decimal difference between going from the 4th term to the 5th term, and from the 5th term to the 6th term, and from the 6th term to the 7th term. How much error there is between that. And as the values get larger, as n gets larger, the error is going to get smaller and smaller and smaller. Okay, because remember, this is an approximation. This is a polynomial approximation to the actual value at a specific point on that function. Okay, are we good?
Yeah.
Okay.
Thank you.
If you have any other questions that come up like on Thursday, let me know and we'll spend a lot of time on that. Okay.